Okay, this is Unit 11. We're going to talk about the periodic table. Okay, so the periodic law says that the physical and chemical properties of elements recur periodically with increasing atomic number. So as this table is laid out, according to increasing atomic number, 5, 6, 7, 8, 9, 10, that there's these repeating properties, which is why it's laid out the way it is. So within a group, elements have similar physical and chemical properties. Okay? So periodically means that something repeats in some predictable way. Mendeleev, that good-looking guy right here, is a Russian chemist. He's considered to be father of the periodic table. He put together the table organizing the elements back in 1869, and at the time there were 68 elements. He organized them by atomic mass, with new rows formed to allow elements with similar properties to line up. Okay. Mendeleev predicted that 3 elements would be discovered and have certain properties, and he actually left spaces for them in the periodic table that he published. They were gallium in 1875, scandium in 1879, and germanium in 1886. And the fact that he left these spaces in the periodic table predicting that these elements would be discovered, and then having them actually be discovered, is what gave his table the credibility to become widespread in acceptance. So this is what his table actually looked like, and as you can see, there are some blanks. He has 7 groups. He actually lists 8 groups, but there's no noble gases here. These are just some of the elements, transition elements here. At the time, noble gases hadn't been discovered, and he actually denied the existence of noble gases when they were discovered. But so he had the first couple rows are the same: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and the order is pretty much the way it is today, with some exceptions. Moseley came along, a little better looking guy, and he rearranged the periodic table and ordered it in atomic number order. So why didn't Mendeleev put his periodic table in atomic number order? Well, at the time, atomic number refers to the number of protons in the element, and at the time that Mendeleev put his table together, the proton had not been discovered, so there was no such thing as atomic number at the time. So the only thing that was reasonable to put it together by was atomic mass, which is what Mendeleev used. So here is the periodic table. It's probably the world's best cheat sheet. It's got a ton of information if you know how to use it. It's organized by groups which go down. This group, this group. So the groups go down and the periods go across. Period 2, period 4, period 7. It's also organized by metals, metalloids, and nonmetals. So in the yellow here, on the left side of the periodic table are the metals. On the far right are the nonmetals, and in between are the metalloids. These green along the stair step are the metalloids. Okay. All right. So let's talk about the properties. So metals, as we know, are left with a staircase. So as we know, metals are good conductors. They conduct both heat and electricity well. Most of them are silver. They have high luster, meaning that they're shiny. Malleable, which means we can hammer them into shape, form them. Most of them are solid at room temperature, and they form positive ions or cations. Nonmetals, which are the other extreme on the right side of the staircase, are poor conductors. They do not conduct electricity or heat. Most of them are gases at room temperature. Those that are solids are brittle, and they form negative ions called anions. And then along the stair step are the metalloids, which have properties of between metals and nonmetals. They tend to be dull. The solids are brittle, but not quite as brittle than the non-metals. And some of them are semiconductors, have some nice properties, and are therefore used in electronics, specifically silicon. Okay, the octet rule says that atoms react by gaining, losing, or sharing electrons so as to acquire the stable electron configuration of a noble gas. And that means a full valence shell or outer shell of electrons, and that usually means 8. Although with helium, as you know, it only has 2 electrons. So the reason atoms bond, which means gaining, losing, or sharing electrons, is because they want to get to that stable, low energy configuration that a noble gas has, which means a full outer shell, full valence shell. Alright, so metals tend to lose electrons. They form a positive charge known as a cation. So group 1 to 13 tend to lose electrons, and sometimes 14. Nonmetals tend to gain electrons. They form a negative charge. They're known as anions. In groups 15 through 17 and sometimes 14 will become anions or negative charged ions. We've looked at this before. We look at the periodic table. First group is going to form an ion of a charge +1, +2. Go all the way over here to where boron is, it's +3. And then starting from the noble gases, 0 here, they're not going to gain or lose electrons. Fluorine has 7 electrons, it's going to gain 1, so it's a -1 charge, -2, -3. And then in the middle here is where carbon is, and they're going to, if it becomes ion, it will be a +4 or a -4, but these elements more often are involved in covalent bonds and not ionic bonds. Whoops, let's just go back for a second. And in here in the center are the transition metals, and they have different charges. Mostly they will have a +2 ion, but they will also have other ions. And the charges are almost always positive. So these are all metals, and they become positively charged. They lose electrons. So if we look at the periodic table of the elements, we're going to look at what each of the groups are. So the first group is known as the alkali metals. It's this first group here in orange, not counting hydrogen, okay, just the orange group. And alkali metals have 1 valence electrons. They're mostly silver in color. They are soft, can be cut with a knife. They are extremely reactive, and because they are so reactive, they're not found in nature because they will combine with some nonmetal and form a stable compound. Okay, alkaline earth metals come next. They're here in yellow. That's group 2. They have 2 valence electrons. They are harder and denser than the alkali metals. They have a higher melting point than the alkali metals. They are very reactive, but not quite as reactive as the alkali metals. And because they are still quite reactive, they are also not found in nature because they will react with things around them. And then we have the transition metals, which is this whole pink area here. And they all have 2 valence electrons. They are good conductors of electricity and heat. They have high luster, which means they're shiny. They are harder and denser than group 1 and 2. Okay, and they are less reactive than group 1 and 2. So they are not as reactive as these 2 groups here. And because they are not reactive, some of them are actually found free in nature, and you're probably familiar with those things like copper and gold and silver. You can actually mine for those. And then way over here in group 17 we have the halogens, and they have 7 valence electrons. They are the most reactive nonmetals. Fluorine and chlorine are gases at room temperature. Bromine is a red liquid at room temperature. And iodine is a dark purple solid. Astatine is actually a synthetic element, so it's man-made. So really very, very diverse in terms of its physical properties. Then we have the noble gases over here on the far right. These all have 8 valence electrons except helium, which has 2. So they have a full valence or outer shell. And because they have their 8, they are unreactive. They do not need to combine with other elements or lose or gain electrons because they have what makes them nice and stable, which is 8 valence electrons. And they are all gases at room temperature. So these elements down here are called the inner transition metals. And on the top row we have lanthanides, and we know, remember that because they start with lanthanum. So these are the lanthanides. Top row of the bottom section here, they are shiny, they are reactive, and they are metals. The bottom row of the inner transition metals are actinides, and they are on the bottom row. The first 4 of them are found in nature all the way up to uranium. And the others are all synthetic, so they are not found in nature, they are all man-made. And almost all of them are radioactive. And some of them have very short half-lives, which means that they only are viable for seconds. Okay, hydrogen kind of stands by itself, so we talk about that separately. It is located in group 1, but it is not a metal. Okay? And it is a gas at room temperature. So you might wonder why we call these guys down here the inner transition metals. The periodic table is actually really designed to look like this, where these 14 across here, the 2 rows of 14, belong right here in the periodic table. The problem, of course, the practical problem with having this is that when we had the periodic table arranged like this, it'd be a really, really long table. So to make it more something that can be displayed, someone had the idea to take them out, take these out from here and put them at the bottom of the table. But they actually belong right up here. And sometimes you will see lanthanum and actinium up here, and sometimes you'll see it down here depending on your periodic table. Okay. All right, so that's going to do it.